At the end of the analysis, you're going to have to figure out the uncertainty in each of these variables. H would be the height of the block. L would be the separation between the supports. These two things together create sine theta. We need to have the uncertainty in displacement and the uncertainty in time. All those are going to be dealt with as relative uncertainties to find out what is the uncertainty in our final value for g, the acceleration due to gravity. So this page is in your lab manual, and you need to carefully write down what it is about the height measurement. What are the uncertainties in height? What is the height? So that you can find this ratio of uncertainty in height divided by the height. And same for the distance between the supports, the displacement, and the time. So let's look at each of those measurements today carefully to find out the uncertainties. We're going to measure this height right here just for the 2x4. We don't really care about the height of the leg, but the 2x4 we want. And we're going to use a vernier caliper to take that height measurement. Every time you take a measurement, remember, you want to discover the uncertainty by asking 3 questions. The first question is about the readability or the resolution. Okay, and the resolution of this vernier caliper is 0.05 millimeters. What is that in centimeters? 0.005 centimeters. What is that in meters? Because that's how we're going to record our data, is in meters. So figure that out in meters, plus or minus how much. That's the uncertainty in the height measurement. To measure the height, you could either choose to use the plunger on the caliper, so we could just plunge down the side. That's kind of hard to keep it perpendicular. So you're probably better off just taking the block out and measuring the height with the vernier caliper. Remember that you tighten it down and then you can remove the block, okay, as long as you've tightened the thumb screw. Please don't take these thumb screws off. Then you're going to measure that height. And you should know that we bought these at a very high price because they're precision blocks. Okay, they're extremely uniform along each edge, and there's 90 degrees exactly here. And yeah, are you believing that? Anyways, it's kind of overkill. My father-in-law is fond of saying, measure with a micrometer, mark with a crayon, and cut with an axe. Yeah, figure that out. So we're going to put this back after we've taken that measurement. The uncertainty in the height divided by the height is the relative uncertainty in height. And you can multiply that by 100% to state it as a percentage. The next measurement that we need to contend with our uncertainties is the distance between the supports. We have this leg right here. There's the leg in the middle, which is not being used, and then we have the leg at the far end. If we know that distance, and if we know the height of the block, we can actually find sine of theta. Now again, we don't need to know the height of the legs themselves. Now if you're not sure why, look at this drawing. Okay, the legs are not part of the triangle that describes theta. Okay, theta is the angle between the incline and the table. But if we're lifting up one of the legs with a block, all we need to know is the height of the block. And we need to know the distance between the supports. To find the uncertainty in the distance between the supports, it's a 2-point measurement. And each point is going to have parallax. Remember, there's 3 questions we can ask regarding uncertainties. The first one is resolution. The resolution of this metric is 1 millimeter. Now, if we can touch our object to the scale, we can use half the smallest marking. So that would be plus or minus 1/2 millimeter. But remember, we have 2 measurements. It's a 2-point measurement here, and all the way down here is the second point. So if that one has a plus or minus 1/2 millimeter uncertainty, and this one has a 1/2 millimeter uncertainty, then the total uncertainty for the distance between the supports is plus or minus 1 millimeter. The second question we have to ask when it comes to a measurement is, how do we interact with it? The resolution is 1 millimeter. We can cut that in half for our uncertainty, but we have to double it again. What about the interaction? When we actually try to take this measurement, well, there's parallax involved because the leg is not touching the scale. There's a different height here between the top of the leg and the scale, and there's a separation. And so I would venture to say that our uncertainty is much bigger than a 0.5 millimeter. In fact, we might have to say it's a whole millimeter uncertainty down here. Maybe when you take this measurement, your interaction shows 2 millimeters of uncertainty. All you have to do is find out how you're going to take the measurement and then just move your head back and forth just a little bit. And how much does the measurement vary? Okay, so that's the interaction. The third method we will not employ for this measurement, but it's repetition. If we repeat the measurement over and over and over again, then take a statistical standard deviation, but that's kind of pointless here for this 2-point measurement. So it's either going to be resolution or the interaction that's going to answer our uncertainty. I would tend to go with the interaction because of parallax. It's not going to be a 0.5 millimeter, it's going to be bigger than that. So we'll take that uncertainty and divide by the distance. How do you find the second point? Well, we'd like to measure from center of this leg to the center of the leg at the other end. But we don't have a mark for the center here. So instead, we're going to measure from the inside here to the outside of that leg. So the far end of that leg. If we go from the far end there to the near end here, we've just simulated center to center. So take that 2-point measurement, that's going to be your distance between supports, that goes in the denominator, and then in the numerator you're going to put the uncertainty in distance between supports. That uncertainty is the sum of this uncertainty and probably the same uncertainty down there. And I'm guessing it might be plus or minus 2 millimeters here and plus or minus 2 millimeters down there. Maybe you did a better measurement and you have plus or minus 1 millimeter here and plus or minus 1 millimeter down there. If you used a protractor to position your glider every single time, well, first of all, what are the 3 questions we have to answer when it comes to uncertainty? The resolution or the readability, the interaction, do we have any problems using the scale that way? And then thirdly would be repetition, repeating this many times and finding the statistical standard deviation. So in this case, this scale, it's the same one that we use for the legs. It has a 1 millimeter resolution. So we can cut that in half and maybe measure to within 1/2 of a millimeter. But I think you can see right away that our interaction has a problem with that because there's a space between the bottom of this card, plus the card is curved right there, and the actual scale. So the readability probably just goes out the window. So interaction. How does this interface? If I can position this and put it right at 80, I still have some parallax. So you need to discuss amongst your lab partners, what's the uncertainty for the start position? Remember, this is a 2-point measurement, and in this case, unlike the position of those support legs, the start position is probably going to have a different uncertainty because of that interface. It's going to have a different uncertainty than the final position down there. So discuss amongst yourself, what is the uncertainty of the start position? And write that down. Down here at the end of the motion, we have what's called the final position. And there's uncertainty in this final position, just like we had with the start position up there. Part of that uncertainty comes from the serious parallax, where our final flag is out here and our metric scale is way over here. So we have parallax involved. So right away, the resolution, plus or minus 1 millimeter or 1/2 millimeter, we cannot use. So we have to go right to the second question of interface or interaction to make our measurement. To find this measurement, we have another problem. So let's say my hand is here and I've carefully positioned the hand and then somebody's taped my hand down so I don't move it. No, I'm kidding, but you see there's a problem there with the positioning of it. And then secondly, I've got motion. Did you see my hand move when the cart hit? And the faster this is moving, the more my hand's going to move. And I've got this stopwatch here, and I'm stopping the stopwatch. There's probably some uncertainty here that's a lot bigger than 0.5 millimeter resolution. There's parallax involved, or there's actual placement of my hand. So what's the uncertainty down here? It's probably bigger than the start position. Let's say the start position is 1 millimeter with parallax. This one might be 3 or 4 millimeters because there's motion, and it's hard for me to resolve where that stop position is. Okay? We could circumvent that problem with a laser gate right here, a light gate, that as soon as the glider broke the light gate, oh, maybe that's something you can answer later in the analysis. How could you improve on the uncertainties in this experiment? So you're going to take the start position, uncertainty, and add to it the final position, uncertainty. That's your uncertainty in displacement. And then you'll divide by the actual displacement, maybe say the average displacement. And that will be your relative uncertainty in displacement. This stopwatch has 2 different modes of recording. You can hold this recall button here, and it'll switch to the other mode. So this is minutes, seconds, and decimal seconds. For this experiment, we're not going to have any minutes involved. We're just going to have seconds. So this is measuring seconds, tenths of a second, and hundredths of a second. When it comes to my uncertainty in the motion of this cart, when I'm measuring the time, I've got some problems to deal with. So let's ask the first question of uncertainties. What is the resolution? What is the readability of this stopwatch? And it looks like it's at the hundredths of a second mark. So we could say that the uncertainty in time is plus or minus 0.01 seconds, or 1/100th of a second, or 10 milliseconds. That's the resolution of this stopwatch. But how many of you believe that that's actually possible? Let's reset this and see. I'm going to stop it within 1/100th of a second. Oh, that didn't work. Let me try that again. Yeah, you get a little tipsy, after a couple of these, and how long do you think that reaction time would be then? Oh, so we have an interface problem. We're interacting with the measurement, and we find that the resolution of 0.01 seconds is no longer valid, because I can't even start and stop this in 0.01. What is my average here? It's not anywhere near the resolution of the stopwatch. Okay, so I have this thing called interface or interaction with the equipment, and what enters in is reaction time. So resolution is out the window. Reaction time is a problem because I'll have a different reaction time than somebody else. Well, we can circumvent that by just having the same person record the measurement every time. And we even have more reaction time problems than this, because remember, the person holding the stopwatch is actually down there with their hand at the final position. Who's ever releasing the card is somebody else. And that somebody else is saying 3, 2, 1, go! And you see there's time. There's time for you to say go, there's time for it to go through the air, there's time for the other person to hear it, and there's time for the other person to send a signal to their finger. And boy, there's a lot of time involved there. Maybe it's not too much, but on 1/100th of a second, yeah, we're probably blowing the lid off of that resolution again. So we're finding out that the interaction or the interface has lots of problems. And we have more problems down here because this guy or this gal down here is getting a little bit nervous of that cart flying. And so they're anticipating stopping because they're nervous about getting bruised. No, it's not that fast, but this is just wrought with problems. Whatever. There's problems with the interaction. So we're going to employ a third method to deal with the uncertainty in time. We're going to drop this cart 3 times from each position. 1, 2, 3. And measure the time of fall for each of those drops. We're going to take those 3 times and find the uncertainty from those 3. Okay, it's what I would call a cheap standard deviation. When you only have 3 data points and you find the uncertainty, well, you can't trust the uncertainty too much. You mean there's uncertainty in the uncertainty? You betcha. but we'll just suffice with 3 measurements today because that would take a long time to take, say, 100 measurements at each position. So again, we're going to use the third question for uncertainties to find the uncertainty in the time value, and that is repetition. We're going to find that uncertainty in time and then divide by, say, maybe the average time for all the trials. There's different ways that you could deal with this. So on this worksheet, you want to write down all the work that you're doing to find the uncertainty in height. That's the delta height divided by height. Write down all the work and the final result that you have. And then the distance between the supports, the length between the legs. You want to write down all your measurement information there. And then the displacement of the cart. What is the uncertainty in the cart, and what is the distance that the cart traveled? Again, you can just use maybe an average displacement, okay, and find that uncertainty in displacement, which was a start uncertainty and a final uncertainty, the start position and the final position. And then you want to find your uncertainty in time using the statistical standard deviation, and then multiply that by 2. Why? Because in our final analysis, we have what? We have d versus t squared. Okay, and since we're squaring the time, the rules of error propagation say that we have to double our uncertainty. Once you have all those, you can simply add them up. Because they're relative uncertainties, we can add them. And that will be your relative uncertainty in your value for g, the acceleration due to gravity.